So you're talking about the work kinetic energy relation. So the way we had understood this is that if a combination of forces is acting on a body, so number of forces are acting, then the net force, that is the vector sum of all the forces acting. There are, let's say, n number of forces acting. So this net force is equal to mass into acceleration as per Newton's second law for a body of fixed mass. Okay. Mass is fixed. So this is Newton's second law. Now, for such a moving object, if we take dot product with ds on both sides, we get this kind of a relation. So now imagine a body is going on some kind of path like this, or a particle is going on some kind of path like this. So during a very small differential displacement ds, if the acceleration vector of the particle or body is like this, such that this angle is theta, then you can see that a dot ds here will be a ds cos theta, which we can write as a cos theta into ds, which is nothing but tangential component of acceleration into ds. So let's elaborate on this point and understand this better. So here at is a cos theta. It is the component of the instantaneous acceleration vector along the displacement vector ds. So it is what we call the tangential component of the acceleration. Okay. So ds has the same direction as v. So whatever is the instantaneous velocity of the body or the particle at that instant, that will be along this. So a dot ds is the same thing as tangential component of acceleration into ds. So further, now we can see from that since the tangential component of acceleration is dv by dt, okay, it's rate of change of speed. So we have which we can write like this, which we can write as this. Okay, so with this step in place, now we can see that this quantity, the right hand side a dot ds, this has been now reduced to v dv. So integrating both sides of the equation over the path, the left hand side gives us the net work done, the right hand side gives us mv dv integrated. So we can see that this is going to give us the work energy theorem now, that the net work done is equal to half mv square from the initial condition to the final condition. So that is the net work done is equal to final kinetic energy square minus initial kinetic energy square. I mean, final kinetic energy minus initial kinetic energy. So from there we get the statement of the work kinetic energy theorem, that net work done is equal to change in kinetic energy. This is the change in kinetic energy, and this is the net work done. Okay, so just make a quick note of this to recap this part, and then we will look at more examples and application of this. Okay, people. So now let us look at.
Sir, it is pending.
Sir, 1 minute, sir.
Okay. Okay. F dot S. Scroll down further. Okay, people finish with this?
No,
No,
sir.
sir. No, sir. 1 minute.
Sir, usually the tangential acceleration is in the path of ds, no, usually.
It's not usually. That is the definition of tangential vector. Tangential acceleration is the component of acceleration which is along the differential ds displacement or along the velocity. Whereas normal acceleration, a sine theta, that is the component which is perpendicular. Understood?
Yes, sir.
The acceleration vector, if the immediate velocity vector at a given moment is like this, okay, but the path of the particle is not a straight line, it's turning like this. So that means the velocity vector also has to turn. That means the acceleration vector has to have a normal component. Only in straight line motion, the acceleration does not have a normal component. It only has the tangential component. Okay, generally speaking, other than straight line motion, in all other types of motion, whether it is a projectile path or a circular path or whatever, the acceleration has two components, the tangential and the normal component. Normal, or you can also call it the centripetal component. So the tangential component is dv by dt. It's the rate of change of speed. Whereas the normal component or centripetal component, that is v square by r, where r is the radius of curvature. Same thing that you learned in circular motion also, right?
Yes, sir. Yeah.
So this is the important thing. This is the tangential component of acceleration. This only is our E cos theta here, where theta is this angle. Okay, finish with this now. Yes, people finish writing this down, I hope.
Yes, sir, done.
So let's look at the application of this work kinetic energy relation now. So for example, we have something like this. Suppose we have a smooth horizontal surface, and on that we have a given block which is initially at rest. So this is a smooth surface. This is a block at t equal to 0, it is at rest. Okay. Now we start applying a combination of two forces on it. One force is pulling it like this, and we have, let's say, another force which is pushing it like this. So these forces are F1 and F2, and they are acting such that this angle here is alpha and this angle here is beta. Okay. So given mass of the block is 5 kilograms, okay, F1's magnitude is 20 newtons, alpha is 37 degrees, F2's magnitude is 15 newtons, the angle beta is 53 degrees. Okay. Now after some time, the block has reached here. At some time t, its velocity we have to find out, where we know that the displacement from here to here. Okay. And while this block is moving, we are continuously applying these forces. So initially, at t equal to 0, the block was at rest. Now F1 and F2 are constant forces acting continuously as shown. So if at some point of time the displacement, if at time t the displacement has become 10 meters, find work done by F1, work done by F2, speed v of the block when the displacement is 10 meters, at the instant when the displacement is 10 meters. Okay. So just try out this question, people. So for the first part, it's very easy. First and second part, you have to calculate the work done by two forces, and the two forces are indicated to you to be constant forces. So it's going to be pretty easy for you to work out how to calculate the work done. And for the third part, where you're finding the speed of the block, you don't have to use Newton's laws, find the acceleration, and then use kinematics that v square is equal to 2as. Instead, you directly apply the work kinetic energy relation, which we discussed above, that the net work done equals the change in kinetic energy. Okay, so let's.
So one second.
Sir, 1 minute.
Okay. You're working out the first part and the second part, all of you.
So first and second are done. Working on the third
Those are
one.
done. Only
Send
the
me the
last one,
answers.
yeah.
Send me the answers, please.
Oh, yes, 1 minute.
Yes, sir.
Okay, very good, Ethan and Krish. Your answers are correct. Anybody else? Okay, so see the displacement of the particle or the
So one
position
second.
is in the
I'm
horizontal
about to do the
direction.
first part.
Yeah, I'm still talking about the first part only. If you've done the first part, just continue to the third part. So this angle here is alpha, this angle here is beta, and these two are at 90 degrees. So you can see that the work done by F1, that will be F1 dot S. So that will be F1 S cos alpha. So that is 20 newtons into 10 meters into cos 37, which is 4 by
Excuse
5.
me, sir. Sir, I sent the answer in the chat box for the third one. So, yeah.
Okay, just checking. Yes, I've got some more answers. Okay, Ginil, your answer is almost correct, but I don't know, you might have taken cos 37 some slightly different value. We'll take it as 4 by 5 as the standard value. Okay. Yeah, Ethan, your answer is correct. Very good. Krish, correct.
So the third one is correct. Mine.
Yes. Okay. Now, as far as F2 is concerned, the one will be F2 dot product with the displacement. So F2S cos beta. So that is now 15 into 10 into cos 53, which is 3 by 5. Okay. So plus 90 joules. That is the work done by the second force. Because the work done by the first force is plus 160 joules. It should be joules. Now for the third part, you just use work energy. Now net work done is equal to change in kinetic energy. Use this. Okay. Now net work done is the work done by all the forces. So F1 plus F2 plus, in general, you can see there are two other forces acting, weight and normal reaction. But you realize the work done by these two is 0 because they are acting perpendicular. 0 because they act perpendicular to the displacement. The forces are acting perpendicular to the displacement. So the net work done only is becoming how much? It is 250 joules. Okay. And change in kinetic energy will be half mv square minus 0 because the initial speed was 0. So 250 joules is equal to the change in kinetic energy. And the mass I've given you as 5 kgs. Just use that to find the value of V. Quite a simple calculation now. So this is net work done. Okay. Therefore, 250 joules is equal to half mv square. So V is equal to 2 into 250 divided by the mass, which is 5 kg square root. So V is 10 meters per second. Yes, that's correct now, 10 meters per second. Okay, people, so hope this question is clear to all of you. Any doubts, please let me know. Okay, now let's look at the next level of question using, yes, better.
In change of kinetic energy, like how do you get half mv square minus?
Minus 0?
Yeah, like in the
Because
change
see,
of kinetic energy.
so change in kinetic energy is what? Basically final kinetic energy minus initial kinetic energy. So final kinetic energy is unknown to me because V is not known. So I've left it half mv square. But initial velocity was known to me because the question said it started from rest. U is equal to 0. Understood? No? So because the question said that the body is starting from rest. If we did not know that, then the initial kinetic energy would have been unknown quantity. But here it's known that it's 0. Okay.
Yes, sir.
Okay. Okay, now next let's look at a different level of question, but involving the same concept. Okay. Now this was a question that involved only constant forces, and the body on which they were acting, that was moving along a straight line, horizontal straight line, in fact. Okay. Now next question, we have something different. We have this kind of a surface. It's an irregular slope. It's not like an inclined plane, but it's an irregular slope, but it's a smooth surface. So now from somewhere here, let's say a particle of mass m is released at t equal to 0 from rest, and where it is released, the height of the particle from the ground level is h. Okay, so it's released at t equal to 0 from here. Now obviously this comes sliding down this surface, and then eventually at some point of time is going to come here and strike the ground below or whatever with the speed v. So we're going to strike the ground here at a speed v. So given that a particle of mass 2 kg is released at t equal to 0, okay, from a height of, let's say, 20 meters as shown. So first of all, find the work done by each of the forces acting on it. From the start at time t equal to 0 to the instant when it hits the ground. And from that, we want to find the speed of the particle. So again, you can see this is going to be an application of work energy or work kinetic energy relation. But the difference is this time we're not dealing with a situation where it's a simple motion along a straight line. So we have to be a little careful about how we apply the work kinetic energy theorem.
Sorry, here we will have to integrate, no?
Now think about it carefully. Do you need to integrate? So which forces we are talking about when we say find the work done by each of the forces? How many forces are acting on the body?
Sir, 2.
Which are those two? Gravity and
Gravity and normal reaction force.
normal reaction. Okay. Now let's start with talking about gravity. What type of force we can say gravity is? Is it a constant force or a variable force?
Constant.
Okay. So then do we need to do integration for gravity?
No, sir.
No. Okay. Achha. Now what about normal reaction? What type of force is it? Will it be constant or will it be varying as it acts?
Sir, it can vary, no?
It will vary, you know, because the slope is changing, no? So at every point, the direction of normal reaction will only be changing, isn't it?
Yes, sir.
Okay, so we'll have to use integration. But then one thing is very simple. When we are using integration, when we take the dot product of normal reaction with displacement n dot ds at any point, what you can say about the angle between the two vectors, n and ds? Like see when the
Sir,
particle
can you
is
come again?
sorry, come again.
Sir, I didn't get what you were saying.
Okay, so let's say the particle is at some point of time over here, okay, where I've shown. So what will be the direction of the instantaneous displacement ds in a very small time? It will be like this along the slope.
Yes, sir.
What about the direction of normal reaction? Normal reaction का direction ऐसा होगा ना, perpendicular to the
surface. Yes, sir.
So this angle will always be 90, na?
Yes, sir.
Now by the time the particle reaches here, let's say the displacement ds is now in this sort of direction, but accordingly the normal reaction's direction has also changed, na? So they're always perpendicular. Okay. So one important thing is that though normal reaction is a variable force because its direction keeps changing here. Okay, but at any instant during the motion, n's dot product with ds is how much? It is 0. Because normal reaction will be normal to the surface. That means normal or perpendicular to the surface. And ds will be along the surface, or what we call tangential. Okay, so their dot product will be 0. So these two are perpendicular to each other. So therefore, work done by normal reaction will be how much? It will be 0. Okay, so even though there is a variable force, but we don't have to worry about doing an integration, because before we complete the step of integration, we can see that the dot product with displacement is 0 at all points, n dot ds. And the other force that we have to worry about is gravity. But luckily for us, mg is not a variable force, it's a constant force. So for that, we don't have to do integration. We have to just find the dot product. Okay, so hope this point is clear about the question.
Yes, sir.
Okay, so now work it out. So at any point of time, there are two forces acting on it, mg. But mg is always acting vertically downwards, and normal reaction is always acting normal to the surface. So for mg, we don't need to do any integration. We just need to calculate the dot product. This is one thing, whereas mg is a constant force. Acts vertically downwards. So work done by mg, just do by dot product method. Yes, good, Krish. Okay, so let's complete the calculation. Krish, your answer is correct. So to calculate the work done by gravity, what we have to understand is that as that particle is going on a path like this, whatever this path is, okay, but the displacement is this vector. And when we calculate the dot product of this vector with gravitational force, which is the vertically downward vector, we don't need the vector's magnitude, we just need its vertical component, okay, which is h, because mg is like this. So when we calculate the dot product, we will just need this vertical component of this, which is h. This h will need, okay. So that is going to be 2 into 10 into 20. So work done by gravity is going to be 400 joules. Work done by normal reaction is 0. We've seen that earlier. So that's the first part. The next part, the net work done is equal to change in kinetic energy. So again here, the initial kinetic energy. So the initial kinetic energy is 0. Whereas by the time the particle hits the ground, the final kinetic energy that is the unknown part. So just a second.
So
Yeah, beta, what was your question?
for mg over there, mg is, oh, okay, sorry.
Mass was 2 kg, I think. Yeah.
Yeah, got it.
Yeah, G I'm taking as 10. Okay. Take that one. Otherwise, you can take G as 9.8 also, but here I'm taking it as 10. Okay. So V is becoming 20 meters per second. Okay. So this is another example again of the application of the work kinetic energy relation, that the net work done by all forces acting on a body. In this case, there are two forces only, but net work done is equal to the change in kinetic energy.
So work done by normal, it shouldn't be like, it should be negative, right?
No, but see, that is the point. What is happening? A normal reaction at every part of the journey. Na? If you look at the normal reaction at any instant, its direction is what? Its direction is normal. That means perpendicular to the surface. Na?
Yes, sir.
And this displacement in that small interval of time ds, what is the direction of that? That is going to be tangential to the surface, like along the surface. So then what is the relationship between n and ds? They are perpendicular to each other. Na?
Okay, sir, got it.
You're understanding the point? So though
Yes,
generally it's a very complicated path like this, but let's say when the particle was here, what is the direction of the normal reaction? It's like this. It's along this perpendicular to the tangent. Whereas what is the direction of displacement? It is along the tangent. ds is like this. So they have a 90-degree relationship between the two of them. So now by the time the particle comes somewhere here else, again, individually the directions have changed. Normal reaction has become at a different angle. ds has become at a different angle, but their mutual relationship is the same, that they are perpendicular to each other. Because
yes, sir, got it.
okay, so that is a trick that we use in this type of problem. Wherever a object is moving along some surface and there is no external force acting on it too, or actually irrespective of that external force, normal reaction ka work done will always be zero in this kind of situation, because by definition it acts perpendicular to the surface, and by definition the displacement ds is along the tangent to the surface. So this is like a small trick that we can remember for all such type of problems.
Yes, sir.
So this is a very, so that is actually the whole purpose of doing this question, so that from this point onwards we remember this trick. Okay, so this is done. This question is understood, everyone?
So what is the answer for the second part of it?
V is equal to 20 meters per second. Just kinetic energy को
Okay,
equate
yeah.
करते with the net work done, and 400 joules को half mv square. Put the value of V,
Yes, yes, I got
m,
it.
you'll get the V. Okay.
Okay, sir.
Okay. Now next we come to a very important classification of forces. Okay. We divide forces into two categories based on some property of their work done, and that is conservative versus non-conservative forces. Anyone heard this term before, conservative force? Okay, so
So the
let me
forces in which the final and initial forces are always same.
no, that is constant beta. That conservative is a slightly different kind of definition. It is related to work done by the force actually. Okay, so let me explain with an example or two also. So definition of conservative force, if we look at the word definition, okay, if the work done by a force is independent of the path taken, it means it does not depend on the path, it's independent of the path for its application. Okay, and rather only depends on the position, the initial and final position. Then such a force is called a conservative force. Whereas if the work done depends on the path. That is, the work done will have different values for different paths between the same 2 points. Then it is called a non-conservative force.
Sir, could you please explain both these forces once again?
Yeah, write down the definition first, then with examples we'll understand in more detail.
Okay, sir.
Okay, so now let us understand this with an example. So let's say we are taking two situations like this. One is we have a straight inclined plane and a block is moving from this point A here to this point B here, such that this is some X and this is some Y. Now, what about the work done by gravity from A to B? How much it will be in this case? It will be mgy. Just now we understood why this is the case. Now we'll take the dot product of mg with the displacement, right? Now let's take another situation where we have the same initial point A, but we have this kind of a path, and that's taking us to the same final position B. So what we mean by same initial and final position is that if you look at the coordinates, they are the same. So if you look at the displacement, that is the same, but the path is very different. Now the path down which the body will move will be this kind of a path. Whereas here the path was a straight line path. But what about the work done by mg in this case also? It's the same, isn't it? So in both of these, the work done is the same. So in this example, you can see that the work done by mg from A to B is independent of the path taken from A to B. It only depends on the initial position A and the final position. Work done by the gravitational force mg here. Okay, this is independent of the path. So that means it's coming in within the category of which type of force? It is a conservative force here. It does not matter what path we take the body from, as long as we are taking it from the point A to the point B. Okay, between those same two initial and final point pair, the work done each time by that force, gravity, will be the same. So this is an example of a conservative force. Okay, now I'll show you an example of a non-conservative force next. Then you note down both examples together so that you can see the contrast or the difference between the two definitions. What is a conservative force and what is a non-conservative force? Okay. This is a vertical view. Now, next example we are seeing is a body is made to slide on a rough horizontal surface. Okay. And now we are seeing the top view of that. So in the first case, we take the body on this path from A to B, where this is X and again this is Y. So as the body is moving on this path, by the time it reaches somewhere here, the direction of friction acting on it is in which direction? Backwards. There'll be a friction of mu mg acting backwards like this. Now when the body is moving on this part, okay, if the velocity vector is now in this direction, the friction, kinetic friction, will be in the opposite direction. So it will be mu mg like this. So what about the work done by kinetic friction in this case? The work done by kinetic friction will become minus mu mg x minus mu mg y. So it will be minus of mu mg into x plus y from A to B. Okay, via the path shown. That is a path one. But same thing now, suppose I take it through a different path. Suppose I take it via this path directly from A to B. Remember, this is again the top view. I'm looking into a rough horizontal surface, and this distance is x and this distance is y. Okay. So this time, as the body is moving along this path, its velocity at any instant is like this. But what about the direction of the friction? The direction of friction is along the hypotenuse in the opposite direction. So if this displacement is s, what will be the work done by friction? It will be minus mu mg s, or minus mu mg root of x square plus y square for the second path. So we can see in this conclusion that work done by friction is not the same in the two different paths. Between the same 2 points A and B. Okay. Therefore, we can say that work done by friction is what we call path dependent. It is not independent of the path, but it rather depends on the path. So therefore, friction, kinetic friction, is a non-conservative force here, because the work done by it depends on the actual path taken. Okay, so hope with these two examples, it is somewhat more clear what we mean by the earlier definition of conservative
So could you
force.
just scroll up a little bit?
Yes,
please?
I'm scrolling up. Okay.
Okay, thank you.
So hope with these two examples, it is somewhat more clear what is the difference between conservative force and non-conservative force. Okay. And as we look at more examples and see the application in more number of questions, we'll get more and more clarity about these definitions of conservative and non-conservative forces. Okay. So start by just going through these two examples and trying to understand, okay, what we mean by the work done by mg is path independent.
So can you please explain the non-conservative first example?
Yeah, so see, you're understanding the geometry of the problem. No? Matlab, ek case mein, the first case mein I'm sliding the body from A to B, but not by a straight path, by an L-shaped path like this. This is the actual path taken. Got it now?
Yes, sir.
So when I'm sliding it from here to here, how much work friction is doing? Minus mu mgx.
Yes, sir.
And when I'm sliding it from here to here along that y, the work done is minus mu mgy.
Yes, sir.
So to take it from A to B via this L-shaped path, what is the net work done by friction? Is this much in path 1?
Yes, sir.
Now, instead of taking it from on that L-shaped path, instead of taking this path, if I pushed it directly from here to here, then what would the work done be? It would be this much.
Yes, sir. Got it.
And this is not the same as this, as you know. So therefore,
Yes,
you can
sir.
see that in this case, the work done by friction for two different paths is two different values, even though the initial and final position are the same. So that means the work done by friction is what kind of quantity here? It is a path dependent quantity. Whereas in the earlier example, the work done by mg was which type of quantity? It was a path independent quantity. So if work done is path independent, it is conservative. If it is path dependent, then the definition is that it is non-conservative.
Yes, sir.
You understood this, no? Good.
Yes, sir.
So can you zoom in the conservative force example?
So could you scroll down please for the statement? Very good.
Okay, so now let's discuss a little bit more about
One
conservative.
second, one second. Sir, I will copy from the notes.
Okay. Okay, so another important point to understand here is that all constant forces are conservative because work done is given by F dot S for a constant force. Okay, and this is path independent. It does not depend on the distance and the path. It only depends on the displacement and its relationship with the force. Variable forces can also be conservative. Example, spring force. Now we had seen in the last to last lecture that work done by spring force at x equal to 0, the spring force is 0. But at x equal to some positive value of x, the spring force becomes minus kx. At x equal to some negative value of x, the spring force becomes positive of kx. It's like this, okay? When we have some kind of a spring attached to a block. So work done by the spring force is given by this kind of integration, okay? Because this and F we will replace with minus kx because it is proportional to x in magnitude and opposite in direction always. So work done by the spring force is minus half k so initial state of the spring, final state. So work done by the spring does not depend on the path. It only depends on the state, the initial state and final state. It only depends on the initial and final state of the spring. Therefore, spring force is also conservative. So while all constant forces are conservative, we have observed above, but a variable force can also be conservative. And an example of that is the spring force. Okay, the restorative force applied by a spring, that's an example of a conservative force.
Sir, I didn't understand the diagram that you drew right now for spring force.
What is there not to understand, beta? You already know the action of a spring, na? Spring जब natural length पे होता है तो वो zero force लगा रहा होता है. X equal to 0 पे force 0 है. वहां से if you compress the spring, what is the direction of the force it applies? Like this, na?
Yes, sir.
वहां से if you extend the spring, what is the direction of the force it applies? It's inwards. And what is
Sir,
the magnetic?
in the second one there should be negative x, no?
Which second, which first?
Sir,
Extension or compression?
Sir, in
Which
the
case?
compression one.
X is negative, no, beta. So force is positive. What is the direction of the force? Is it the positive x-axis or negative x-axis? See, है ना, x का वैल्यू कैसा है, नेगेटिव है, तो फोर्स का डायरेक्शन क्या हो गया, पॉजिटिव हो गया ना.
Yes, sir.
Okay, you're understanding? This is your x-axis. If this is your origin point, then at some negative x coordinate, what is the direction of the force? It is positive. At some positive x coordinate, what is the direction of the force? It is negative. Hence the two different signs. Here the force is negative when the x coordinate is positive. Here the force is positive when the x coordinate is negative. So in general, what is the relationship between the force and the x coordinate? It is negative relationship. That is why when x is positive, force will be negative. When x is negative, force will be positive. Okay, so that is why we replace F with minus kx in general. So when we use that definition of the spring force to calculate the work done, we come up with this formula. Now this formula shows us that it's independent of path. It only depends on the initial and the final position, that is xi and xf. Okay, so written down this point here. Okay, now we will discuss more about how to determine whether a force is conservative or not. There are lot many methods and it's quite a complex subject, but we don't need to get into that so much over here just now. As of now, we just need to keep 2 or 3 examples in mind. For example, gravitational force is conservative. We've shown above. Spring force is a conservative force that we've shown through this example. Whereas kinetic friction is a non-conservative force that also we've discussed in the example above. So these 2-3 examples of conservative and non-conservative forces, if we keep in mind, it is more than sufficient for solving the questions at this level. But as we come to more chapters in physics later, like rotational mechanics, then later electrostatics, etc., we will once again have discussions about conservative and non-conservative forces, and we will see some more advanced methods related to them. Now, currently, we will look at the next thing related to conservative and non-conservative force. Okay, why we have gone through the trouble of understanding the definition of conservative and non-conservative force. Let's understand that also. But before that, one more thing. There is an additional property of conservative and non-conservative forces, which we should understand. The work done by a conservative force in what is called a round trip. So what is the meaning of a round trip? It is such a path where on completing the path, we are back to our starting position. That means the initial and final position are the same. That is the meaning of the term round trip. Okay, so a round trip is a path such that on completion, okay, the final position is back to the initial position at the start. That is the literal meaning of the term round trip. It doesn't matter what the shape of the path is, but if it is a closed path where our initial position is equal to final position. Okay.
Sir, then work done should be 0, no?
Yes, very good. That is the for a conservative force, closed path or round trip. So in any closed path or round trip, okay, the work done by conservative force will always be 0. Okay, so this is one very important property of conservative force, that the work done by conservative force in a round trip is always 0. Whereas for a non-conservative force, the work done in a round trip is non-zero. Okay. If you slide an object along a round trip on a rough surface, the work done by kinetic friction will be a negative quantity. It will not be 0 because throughout the path, the friction is doing negative work in each and every section of it. Yes, Beta, what's your question?
So, but like if we go by the definition of work done, it's like force into displacement, and in a round trip we have
No, Beta, the
distance.
definition of work done is not force into displacement. That is the whole point you have to understand. The proper definition of work done is it is path integration of force. Got the point? It is this.
Okay, sir.
From now on, we have to use this as the general definition. We can say it is force into displacement in the direction of force or dot product of force with displacement and all that, only and only in the special case where the force is constant. Okay, and we've already seen that a constant force is conservative, isn't it?
Yes, sir.
Okay, but the general definition is what it is, F dot ds. So it is always possible that we have a variable force for which what will happen, the work done in a round trip will not be 0, like the case of the kinetic friction, the example I've told you already, So imagine
Yes.
a particle sliding on a circular track on a rough surface. When it completes one full circumference, okay, is gone through a round trip, but will the work done by friction be zero? No, no, because in every section of the circle, friction is dissipating some energy, it's doing some negative work.
Yes, sir. Got
So
it.
the most natural and easy example to remember about how this situation can happen, कि कैसे हो सकता है कि we are on a round trip, but the work done by a particular force is not equal to zero. Just remember the example of kinetic friction. So it will be very easy for you to visualize how this is possible and why. Therefore, by definition, a non-conservative force does non-zero work in a round trip, whereas a conservative force will always end up doing zero work if we take it back to the initial position. If we are going a round trip, the net work done by a conservative force will always be zero. Okay, so that is about work done in a round trip for conservative and non-conservative forces. So this is, for the moment, everything we will learn about conservative and non-conservative forces as far as definition is concerned. Okay, of course, through application questions, next up, we will look at a lot of other things, okay, and continue to work with both these type of forces, learning more about them, okay. But as far as the theoretical definition is concerned, this is all we need to know. Now, the next thing we will define is something called potential energy. Can you tell me any types of potential energy you have heard about?
So elastic and gravitational.
Yes, elastic potential energy of a spring or any kind of elastic material like a rubber band, right? Or anything which has elasticity, okay. And of course, gravitational potential energy you've heard about, okay. So in general, how do we define potential energy? Potential energy is defined for any mechanical system, or for that matter, any system, need not be mechanical. For example, at a later stage, we will also discuss about potential energy of an electrostatic system, like a system of charges. If we have charged particles arranged in a certain kind of way, that's called a system of charges. And that system also possesses something called electrostatic potential energy. However, here we are talking within mechanics. So by a system, we basically mean a mechanical system. Okay. So potential energy, which we generally denote with the symbol U, capital U, for a given system, okay, is defined as the energy associated with the state of the system. state, or even a better word for it is configuration. Configuration of the system. Okay. So for example, the most obvious example of potential energy, the one we talked about, elastic potential energy. Okay. So elastic potential energy of, let's say, a spring. Okay. So it is the energy related or associated with state. And by the state, we mean by the amount of compression or extension. Okay. Intuitively, we understand that the more compressed or extended, okay, the state of the spring, the larger the potential energy it's storing. And as opposed to that, when relaxed, that is at natural length, it has zero potential energy. So that's an example. Another example of potential energy is gravitational potential energy. Gravitational potential energy, okay, is related to the position, and by position we actually mean the vertical position or the vertical height of a given mass with respect to the Earth's surface. Okay. And again, logically, you would have understood that the higher the height from the Earth's surface, the more potential energy it has, the more gravitational potential energy it has. So in general, for any system, we define the potential energy as that form of energy which is associated with the system's state or configuration. And therefore, whenever we change the configuration of the system, the potential energy gets changed. So if we are making some change such that the potential energy has to increase, that means we have to do some work on the system to increase its potential energy. So like that, if we are having a spring at its natural length initially, so it's got zero potential energy. Now we want to compress it or we want to extend it. So we want to store potential energy in it as we are compressing or extending it. So in order to compress the spring, some external agent will have to do work on the spring, and that work will get stored in the spring as potential energy.
So could you please explain that compressed part?
Yeah, so see, if you compress a spring from its natural length, you have to push it against the spring force. No? The
Yes,
spring
sir.
force will try to restore it back to natural length. So whatever is the external agent who is pushing the spring into compression, no? The work done by that external agent will be what type of work done? It will be positive because you'll have to go against the restorative force of the spring and displace it.
Yes, sir.
So that work done by the external agent only, that work gets stored in the spring as potential energy. So that's why when you compress a spring from natural length to some compression, the spring ends up saving some energy or storing some energy, which is called potential energy.
Okay, sir, got it.
Okay. Now, likewise, the reverse can also happen. Potential energy can on its own always convert into kinetic energy if you allow a system to release that potential energy. And just like if you lift an object up from the ground, you have to do positive work on it to store gravitational potential energy in it. But the moment you release it, it will fall from a height. And as it falls, what will happen? It will be losing gravitational potential energy and gaining kinetic energy. Isn't it?
Sir, when it reaches on the ground and is stable, then which does it have?
No, what happens is when it reaches the ground, it will make an impact on the ground. It will collide with the ground, and on colliding, instead of bouncing, if it just remains on the ground, that means the collision is something called an inelastic collision, in which it dissipates energy. Got it, no?
Sir, so at the end, the energy will disintegrate and go to the
So see,
surface.
suppose if I released a particle from this height. So what has happened at this point of time? We know that the gravitational potential energy, we'll do the proof of this in the next lecture, but we'll see that the formula for gravitational potential energy is mgh, and right now its kinetic energy is how much? 0. Okay. Now suppose we've released it, so it's gone into a vertical free fall from here. So as it falls, by the time it hits the ground, what happens to the kinetic energy? It's become half mv square, but the potential energy has become 0 at the ground level. So what has happened? Going from here to here, potential energy is converting into kinetic energy. So half mv square is equal to mgh. So just before it's hit the ground, how much the kinetic energy is? It's equal to this mgh. Okay, this is clear so far?
Sir, after the whole process
so
is
far this
over
is clear.
and
So far this is clear.
yes, so far it is cleared.
Okay. Now suppose on hitting the ground, next thing what happens is after the collision, suppose its speed has become 0. So that means what has happened to this kinetic energy? This kinetic energy has got dissipated. So it dissipates. That means it gets lost in the collision. So that means it would have converted to some other forms of energy. Like there would be sound energy, there would be some heating. Okay. There might be some crack on the floor also, or some damage to the shape and size of the object. So that means intermolecular bonds have been rearranged because the shape of the material has changed. So kinetic energy has been converted to those other forms of energy. Is it clear now?
Yes, sir.
Okay. So before we come to calculations based on those kind of things, let's observe one more thing. So kinetic energy and potential energy can interchange in any system undergoing a change of state. State or configuration. So just as an example, we'll see, suppose we have a situation like this. We have a block on a smooth surface, which is going at a speed v. Okay, and somewhere down the line, there's a spring, which is at natural length. After some time, what we'll observe that the block has pushed against the spring a little bit. Okay, so its speed v prime, let's say, has become less than the initial speed v naught, but the spring has got compressed. Okay. So as the block is hitting against the spring, kinetic energy of the block is decreasing, and potential energy of the spring is increasing. Okay. In the above example, when we drop an object from a certain height, as it falls through a certain vertical displacement, it loses gravitational potential energy and in the process gains kinetic energy. So free fall is gravitational potential energy is converting to kinetic energy. So like this, in various types of systems, you'll see that there's always an interchange between kinetic and potential energy that is happening when the system is undergoing a change of configuration. Now that can happen both ways. The kinetic energy can be decreasing and converting into potential energy, like in the case of the block hitting against the spring and compressing it more and more as it pushes against the spring. Or it can be the reverse, like in the case of an object in free fall, the potential energy could be decreasing and that is increasing the kinetic energy of the block. Okay. So again, related to potential energy and kinetic energy, and of course work done by forces, there is a second theorem which is called the work energy theorem. Like we've seen the first theorem, the work kinetic energy relation, that net work done is equal to change in kinetic energy. Like that, in the next lecture, we will look at the work energy theorem, which is the relationship between work done, the change in kinetic energy, and the change in potential energy. Okay, so that will be the main area of focus, and through that expression of that theorem and its applications, we will look at most of the numerical problems in the chapter of work by energy. Okay, so that's it for today's session, people. Wish you all the best and have a nice day.
So just 1 minute, I'll write that note.
So shall we leave?
Yes, people, the lecture is done for today. If you need to complete the notes, you can write it down.
Okay, thank you, sir. Bye, sir.
Okay, bye. Okay.